This conference will now be recorded.
Okay.
All right, hang on, let's see here. Select main screen, share, and we'll go to presenter mode, see what happens. All right, is that working?
Oh, yeah.
Okay, good. All right, so I'm going to tell you some about Project 38, which is a multi-agency project, but I'll start out with some of our motivation for doing this. This is always generates a lot of controversy when we say that Moore's law is ending, but because we do believe in there will be more and more, it'll just be through a different means, whether it's chiplets or heterogeneous integration. But when I look at the procurements that we have in HPC, we used to renew machines every 3 to 4 years, and now we're stretching our procurement cycles out to 8 years because we only will field a new machine when we are able to achieve a 10x improvement in performance based on real scientific applications in the machine. And we just have not been seeing the historical growth rate. And this is also depicted in Hennessy and Patterson's chart here from their Turing Award talk. Moore's law, as we knew it from shrinking transistors, is definitely on the wane. And so the approach that we're looking at to overcome that is specialization. And it's, of course, not just some computer architect's fantasy. It's nature's way of extracting more performance in a resource-limited environment. Here we have, the traditional powerful general purpose, so Xeon and Power, Raptors. But when we hit post-Dennard scaling scarcity, we moved to lighter weight cores like the Knights Landing, AMD, Cavium, Marvell, and even GPUs to a certain extent. And here, nature responds here with a couple of dozen really aggressive sparrows. But if we go to post-Moore scarcity, where even shrinking transistors no longer gain, it still gets us a benefit, but just not as much of a benefit is derived from that anymore. The critters, they basically have to pursue different food sources, and they specialize, and their beaks evolve for that. And that's where things are going with the Amazon, Google, and Apple with their more specialized chips, many of which based on ARM technology or completely bespoke, like the TPU at Google. So we've been looking at what industry is doing. So certainly this is a dye photo of the Apple A-series chip, and you can see that a large fraction of the area is going to these out-of-core accelerators. And this is Sophia Shao, from Berkeley. And the number of out-of-core accelerators has been growing over time. In 2016, they identified 29 different heterogeneous accelerators, and now in the A11, which was 2017, that's risen to 40 different accelerators. And so, these cell phones and even mega data centers are moving towards this kind of specialization, but we've been kind of slow in the uptake in the HPC space. So this Project 38, we're trying to understand what industry is doing and see how we can apply that to continue to accelerate specialization and also make it practical or affordable for us to apply those kind of techniques to HPC problems. So, in general, we're seeing the future of post-exascale computing moving towards extreme heterogeneity, but what are the right specializations to include? What is the cost model? Because we know we can't afford to spin all of our own chips from scratch. We gave that up 2 decades ago. And we've got, for example, the ARM and the embedded ecosystem taught us that the IP is the commodity, not the chip. And potentially with chiplets, it may be the chiplet is the commodity, not even the IP so much. But we need to understand what are the right partnerships and what's the right economic model for the future of HPC. Neil Thompson, who's a friend of ours from MIT CSAIL, he's also He's the only person I know who has a dual degree in computer architecture and economics. And so they have a recent article here. There's plenty of room at the top about this shift from a transistor focus, where transistor scaling led to better performance and cost, which led to market growth and new investment. And that was the virtuous cycle of Moore's law, since Moore spoke of coined the term Moore's law back in, well, didn't coin the term Moore's law, he coined the term cramming more transistors onto a package back in 1972. But as we move away from Moore's law, being shrinking of transistors being the driving factor, we're seeing technology, device, and circuit innovations and advanced packaging technologies are enabling us to increase functionality and lower cost and improve investment. And this new system-focused virtuous cycle is going to be the new Moore's law, so Moore's law 2.0. And that requires co-design of software together with algorithms, together with the hardware architecture. And this hardware software co-design, this is something that we've been pushing in the DOE, to drive the future of HPC for a while. But we're going to need to even get closer, tighter integration of algorithm understanding with hardware architects, whereas in the past, with x86, you could keep each of these siloed in their own lanes. That's no longer a viable approach to designing the next generation of systems after exascale. And so you should visit Neil's website, neilT.com. Very interesting articles on the economic impact of Moore's law, what's going to drive performance in the future, and also the decline of general purpose computing as the basis for a lot of our technology. All right, so Project 38, DoD and DOE, we recognize that there's this imperative to develop a new mechanism for engagement with our vendor community, particularly in architectural innovations that have strategic value to the US government HPC systems. And so we have a near-term goal to quantify the performance value and identify potential costs of very specific architectural concepts against a limited set of applications. We have a long-term goal really to develop an enduring capability for DOE and DoD to work together to jointly explore these innovations, quantify their value, and a stretch goal maybe of working together with industry to create more purpose-built architectures to drive the future of collaborations and investments. And this is divided into an aggressive vendor, which is a very tight relationship with some of our traditional suppliers, but looking at alternative approaches and economic models to bring specialization into the picture. And the other is innovative US government, where we're exploring the use of some open source, but also using ARM IP, for example, to see what could be done in terms of more tailored system designs, but with the eye towards the economic model that underpins the cost-effective delivery of such systems. All right, so just a basic org chart, so this is Department of Energy, Office of Science, the National Security Agency, and the NNSA, which is the Tri-Labs. We have three vendor engagements and three vendor engagements. So this is who's playing with the three vendor engagements, and then we have our more RISC-V ARM engagement for doing tailored design. So in terms of P38 technology directions, we're looking, of course, just like what's now commonplace in cell phone technology, looking at fixed or really restricted function, I'd say semi-programmable, accelerators and commercial off-the-shelf IP. So, we've got the RISC-V and ARM cores, but we have the Spiral project at Carnegie Mellon is able to generate programmable functionality tailored FFT units, and these FFTs are and other dense linear algebra functions are commonly used in our codes, and so we wanted to see how much we could improve code performance or architectural efficiency by including these things together with programmable cores. The other is word granularity scratch pad memory to support gather scatter operations. Again, tensor contractions very common in our workloads and unavoidable. The other is a recoding engine for a semi-programmable unit from University of Chicago for really branch-heavy code. This comes up in bioinformatics and string matching applications, but definitely for bioinformatics, it's a average 20x improvement over the latest state-of-the-art GPUs and CPUs from something that's only 1/100th the size of an x86 processor core. And the last is lightweight hardware message queues to enable lighter weight interprocessor communication. Again, gather scatter between processor tiles, but also a better interface for, and it enables us to eliminate the overhead of barriers and eliminate atomic operations, which can be quite expensive. And, in terms of our, phase 1 studies, we studied the use of message queues for sparse matrix tri-solves. We're able to demonstrate with architectural simulation, but also more recently with a modified RISC-V core that we could achieve eight times improved scaling. And so it eliminates a lot of the overheads that are, what is it, forgetting the name, the serial portion versus the parallel portion of the code. We were able to significantly improve our strong scaling within a chip by moving to lighter weight communication than using the cache coherence protocol for interprocessor synchronization. The recoding engine, we're able to improve by a factor of 8, 2x to 8x the compression of sparse matrices, and that reduces our need for off-chip memory bandwidth by a corresponding factor. You would not be able to do this kind of compressions at line rate using a conventional microprocessor core because it has too many pipeline stages. So this is a huge win in terms of compression engines. For the fixed function accelerators, we're able to demonstrate just with 14 nanometer technology, and this is as low as we can go with the tools that we have. We don't have a Synopsys license to fully route a circuit we don't have a PDK for less than 14. So, but even with the 14 nanometer PDK, which is fairly obsolete, we can outperform a state-of-the-art AVX 512 CPU using just 4.5 square millimeters of area. That provides equivalent performance to a whole 350 square millimeter Intel chip. And likewise, for the GPUs, we can saturate a 1 terabyte per second off-chip memory interface, get 15 teraflops, which actually exceeds by a factor of 2 what the delivered FFT performance we can achieve from an A100 GPU. But it only uses less than 50 square millimeters of area, whereas the GPU's 700. It's reticle limited. It's over 700 square millimeters of area. So so we wanted to look also at BLAS, which is some dense linear algebra primitives. And then the last is gather scatter. This little diagram here on the right, if you have everything is packed into consecutive cache lines, vector units do very well. However, the moment you start striding, performance collapses. So what we're looking at is having a GPU-like vector engine where you basically have the level 1 cache. Well, really a scratch pad memory is word granularity bank switched. And now suddenly it becomes more ambiguous whether, if you have an ARM SVE, but it's connected to the scratch pad, it looks very much like a GPU, and you can switch it between a GPU and a CPU personality fairly between loops. And with this, we're able to reduce data movement between the level 1 and the level 2 cache by a factor ranging from 55% to 700% reduction in data movement. And in terms of overall the application with all of its different kernels and loops, it's less, but it's still a very significant reduction in unnecessary data movement when you go to this arrangement. Let's skip the conceptual system design. Okay, so the rest of this part, I think, is we're really deep diving into some of these. I guess I didn't need to do this part here, but I'll just talk through the highlights here. When I was talking about the word granularity, scratch pads, a very common operation that we have for finite element multi-physics calculations, and also here on the left, this is a tensor contraction from a chemistry code. You often have your data is sparsely laid out in memory, so you need to do a gather into a dense arithmetic kernel and then scatter things back out after you've completed your calculation. These tensor contractions are again unavoidable because it doesn't matter if you reorganize your data in memory so that everything's dense for one kernel, the very next kernel will require that data in a different order, and there's no real way around that for true multi-physics codes. And so being able to pull in blocks into the level 1 scratch pad, reorganize the data so that it's dense and computing on it and then scattering it back out. Scratch pad memories with word granularity have a huge benefit for this. You can't do this with a level 1 cache because it'll muck with the cache coherence protocol. So this is, why we need these engines. And if we were to do this in a chiplet form, we'd really do the gather scatter engine as maybe a separate unit off to the side where it performs gather scatter on its own and then presents the data in a dense format to a conventional server class microprocessor core, for example. Yeah.
But hey, John, so the vision in your group is that each of these would be accelerators attached to a general purpose CPU, or that's the general, okay.
Yeah. The other is, and this is more, so some of these things are more invasive than others. These message queues that I was talking about are, this would actually, the way that we've implemented these right now is by ISA extensions to RISC-V cores. However, as we want to scale up the number of discrete accelerators, and if we're going to do this thing where we're mixing and matching general purpose cores with these lightweight accelerators, cache coherence is really a terrible interface for interactions, both between the cores, if we're going to scale up the number of cores, but also between cores and accelerators. And so we actually, by extending the RISC-V ISA to include direct messaging between processing elements as a first-class citizen. So we have load, store, and we have message put and message get as primitives. And when you do a message put and message get, the data that you're transferring does not interact in any way with the cache coherence protocol, and so we get a huge reduction in the overhead of interprocessor communication, but also a great reduction in the complexity of the front-end interface required of the accelerator that we're interfacing to. So it doesn't need to speak cache coherence protocol in order to participate in the chip design. And it also has other benefits here. We're seeing that the directed graphs are actually, data flow graphs are very common in a lot of our sparse matrix operations. And they always, when they write the pseudocode for the algorithm for sparse matrix operations, they talk about, they have in their pseudocode receive message, send message, but in fact, no such primitive exists on modern microprocessors. And so this receive data message ends up being hundreds or thousands of lines of code and greatly reduces efficiency. By turning this into something that can execute in 1 to 5 clock cycles, that has a huge benefit in performance for a number of these DAG type algorithms. So this would break inside of a chiplet, but I guess the point is that we think that you should support coherence protocols. They are good, but you should also have a backdoor that does not interact with the coherence protocol and make it a lot easier to integrate chiplets that don't want to speak coherence protocol. This is an example with a sparse matrix tri-solve. This is the data flow. This is basically once you get a lower triangular matrix here, you have to solve for the unknown in the first row in order to get the unknown, the information you need to solve for the unknowns in the second row, and the third, and the fourth, and so on and so forth. And this creates a DAG, a graph of the data dependencies between these elements in that sparse matrix. Now, typically today we just level set the this DAG, and we just have a barrier between each level. This is how it's done in typical OpenMP codes, but this is inherently unscalable. Barriers are not scalable, and also if these elements, like 3 and 2, take a different amount of time to execute, then things really start to bog down. However, if you do this B here in the middle, it requires atomic memory operations in order to resolve whether or not all of your dependencies have been satisfied. By using these message queues, we can actually eliminate the need for atomics, which are very, very inefficient. And by eliminating these atomics, by having direct messages between threads or processing elements to tell when these DAGs are satisfied, we get a much more efficient performance. So here's an example here on the right. When you have 4 cores on a Knights Landing processor, the majority of time is spent in the blue, which is getting useful work done in the doing this tri-solve. But as we grow towards 64 cores, the atomics, the cache coherence protocol starts to bog down. The atomics, you have to check and make sure that no other processor owns that cache line when you're trying to atomically update the count for each of those DAGs. By going with the message queue, we're able to demonstrate right off the bat linear scaling. We're able to return to linear scaling. We eliminate that overhead that you saw in that previous graph, and we can have room to scale another 20x. We don't have a processor that has that many cores, but it definitely almost completely eliminates that overhead and that scaling barrier. This is the stuff from University of Chicago, and this basically shows for these various sparse matrices that we're able to get significant compression factors by using the recoding engine. I should have had more in here to describe the recoding engine. That would be something that would be useful for a chiplet, because it can implement very, very tightly wound finite state machines, which conventional microprocessor cores are terrible at. Sorry, I forgot to update that slide. And then looking at our fixed function or really narrow function accelerator study, this is again adopting a smartphone SoC strategy. We could imagine having a chiplet that targets BLAS levels 1, 2, and 3. So BLAS is basic linear algebra subroutines. This is basically taking all of linear algebra. You can break it down to these primitives like dot product, matrix multiply, matrix vector product. So these are very, and all of those operations are recursive. So you can actually use one fixed piece of silicon, but by feeding it the data in different orders, you can actually implement with a fixed amount of hardware, you could implement, you could do BLAS for any size input data set. And the same is true for FFT. It's a recursive algorithm. Therefore, if you have a small FFT accelerator, then you can implement a very large FFT by presenting the data over and over again as permuted subsets to that FFT unit. And so we used Spiral to generate that, but this would be an excellent opportunity for a chiplet that targets commonly used libraries. BLAS and the FFTW library are two of the most commonly used scientific libraries. So again, like I mentioned earlier, we used Spiral to generate the hardware. We ran it through synthesis using Mentor graphics and the 14 nanometer PDK, and we're able to demonstrate very small amount of area could saturate terabyte per second off-chip memory interface, but consume a very tiny amount of area. And with a more contemporary technology node, we could do even better than that, probably.
I would have a question for the previous slide. When you quote these areas, does that mean that you've actually taped those chips out, or is this like running on an FPGA or something?
No, we only went to GDS. We weren't able to tape these guys out, but we did get to GDS, and then this is where we basically did the power area and timing analysis.
Gotcha. Okay, thank you.
Yep.
One more question, John. You mentioned the previous slide, 1 terabyte per second memory bandwidth off chip. Mm-hmm. How do you achieve that? What kind of interface do you use for that?
Oh, we just basically use that as our model interface. If we were to do that, we'd have to have something like high bandwidth memory. But we actually, this 1 terabyte per second off chip memory bandwidth is just a modeling assumption we made to do this analysis.
Oh, okay, got it. Okay.
Yeah. And again, our aim here isn't to, design a chip and compete against Intel and NVIDIA. Our aim here is to generate solid enough evidence that there's a there that we could partner with one of our suppliers, and we talk a lot with ARM. And as you probably know, there's plenty of IP vendors looking at doing BLAS type IP blocks that are targeting and even FFT targeting blocks to target convolutional neural networks and the matrix multiply you need for a lot of machine learning algorithms. We also did analysis to show, kind of bound by a 900 gigabyte per second memory bandwidth. So we could continue to scale the design up, but there gets a point where you hit the blue area here where you saturate, you can't increase your FFT performance anymore because you've hit that 900 gigabyte per second limit. So that's what the blue boundary is here. And then we have a 250 watt power limit, so that puts up another boundary. And then we have a 350 millimeter squared area limit that shows the boundary for Knight's Landing, but we never really, that ends up not being a limiting factor. So anyways, that's again how we, it's 7.5 times faster than the V100 GPU, which had a measured 900 gigabyte per second memory interface, potentially. So. We also actually took this design and actually used it for a real world application. So we have, this is a cryo-electron microscopy, and this detector, so one thing that we do at the lab, our ASIC design team focuses mostly on generating the instrumentation and detectors for some of our bleeding edge experiments. And so this is the growth in the performance of detectors for cryo-electron microscopy. They're generating, actually this detector has been, it says future electron scattering detector, actually that was built. And it generates 4 petabytes of data per day. It can burst burst data out at like 400 gigabytes per second, I think. And so in order to check the focal plane and make sure that your sample is correctly focused in this thing, requires very fast FFTs in order to process the data. The rate at which it's generated is 100,000 frames per second. So to do FFTs on streaming data that's 2D FFTs and streaming data that's coming in at 100,000 frames a second is a tall order. And it's kind of like this here. And so we took the FFT accelerator that we created for that other design study. We used used a Pico RV32 core. This is a simple RISC-V core, and we added the FFT, the spiral generated FFT accelerator as an extension to the ISA. And we spun this onto, they use U280 FPGAs for the instrumentation for these experiments. And using this, this FPGA, mind you, it's running at only about 100 and, yeah, it's only running at like 50 megahertz, I think. And using a 50, maybe it was 100 megahertz design, we're able to outperform a Core i7 Intel, host, which is running at 3.5 gigahertz, running on the super slow FPGA with RISC-V plus the FFT accelerator is 126 times faster than the x86 host that we were originally using to do this image processing. So if you can outperform a state-of-the-art, Intel chip using an FPGA, then there's a lot more headroom to grow if we were to switch this to to an actual ASIC design. But it shows the power of this approach. So we're looking at a number of algorithms in material science, CryoEM, and here in CryoEM, LBL does design, it has an ASIC design team and it's designing its own ASICs. Genomics accelerator, so we need to do 2 to 8-bit string matching, and so the granularity that GPUs operate at is actually too large for doing efficient string matching for genomics, and digital fluid PDE accelerator for fluid dynamics calculations. So that's kind of what we've been doing in terms of the studying the architecture design space. I wanted to switch gears here and talk about the HPC market, and we do recognize that HPC is this tiny little capstone here on top of a very large Branscombe pyramid, which is founded on the volume market for hyperscale data centers and basically desktop computing. And we've leveraged this 80-20 rule for the past 20 to 30 years. I guess the attack of the killer micros was the mid-90s. And it's done, we've done well by that. We innovate on the parts where, like the interconnect in the IO system, and the rest of the microprocessor is all, commodity. And this was founded in the idea that the chip is a commodity, and we want the broadest base for our Branscombe pyramid. But, the more recently, over the past 10 years, we started looking at the ARM IP market, where, the design and verification costs are really the dominant costs for generating a new chip. And so if you use off-the-shelf IP and you treat the IP as the commodity rather than the chip as being the commodity, then you get additional flexibility in arranging off-the-shelf IP to create next-generation designs. And that's the approach that the RIKEN used for its exascale supercomputing project, the Fugaku, which uses ARM cores with SVE vector, which is fairly off the shelf, but combines it with a high bandwidth memory subsystem, co-packaged memory stacks, and their own custom interconnect design. And so in HPC, we're still able to innovate by creating custom interconnect designs, but the PCIe gets in the way of achieving the full performance potential of those things. By co-packaging, they're able to greatly reduce bandwidth, greatly reduce latency, and greatly increase bandwidth on Fugaku. And so that's a real case in point that maybe we're looking at the wrong thing for the base of our Branscombe pyramid. we should be looking at IP as the commodity, not necessarily the not necessarily just the chip as the commodity. So that's one learning, but then these chiplets have come onto the market, and now we're starting to consider, because physical design is still non-trivial, and whether or not an open ecosystem of chiplets would give us the same leverage of being able to use, but arrange in custom ways, commodity IP, but do so in a chiplet package format, and that open ecosystem may even further improve our leverage points, I guess, for doing tailored designs, where it would be the new 80-20 rule. Is maybe we'd come with one chiplet, but all the rest of the chiplets would come from the open market. And it's not like we have to do the full custom machine that does absolutely everything from the get-go. If you look at the time history of the cell phone market, or really this is the IP, the open IP market, once an IP block has been verified and generated, it tends to get reused across a lot of other applications. So good IP doesn't really go away. It doesn't become obsolete. In fact, the amount of IP reuse over time increases. And so we can have a long-term plan in HPC that we don't innovate everything simultaneously, but we can build up a portfolio of IP blocks or chiplets that are targeted to serve our applications, in addition to being reusable across other places. So we don't have to do a full custom design from the get-go. You build up that capability over time. So reusable IP is a true commodity. Chips aren't the only commodity out there. And the other is, both licensed and open source IP can overcome opportunity cost barriers. Licensable IP, if you can get licensable IP, you should use it, or licensable chiplets. That lowers the barrier, but some IP, especially some of the stuff that we would need for supercomputing, isn't going to make money for ARM, and so ARM isn't even going to offer it in their licensable IP ecosystem. And so, but there is an awful lot of stuff that you need on a chip that isn't interesting but extremely reusable. PCIe root complex, SerDes, memory controllers. Why would open source want to own all of that? Perhaps our new 80-20 rule is to build up a library of open source reusable accelerators for HPC, but they would be the 20% or less part of the chip. For interoperability and sustainability, you would want to work with commercially supported IP, or better yet, a chiplets type ecosystem. So, people have talked about open source versus licensed IP. I say,
hey, John.
Source and, yeah.
So on the previous slide, the one that you just, do you, is there a consortium, or is there some entity that says this is the list of open source? Oh no, excuse me, not open source. This is the list of commercial chiplets we're looking for. I mean, no. I see what.
No, well, yeah, I can generate that list for you. I've been going around one by one to your different members, trying to figure out who's doing what, and it's a very time-consuming operation to do that. I actually have some slides at the end I could show you, like a high-level diagram, but it's not very well thought out. But I can also, working with ARM, we basically, with their Neoverse ecosystem, we basically were able to work out with ARM what precisely the function, the stuff we needed out of their IP design library to create a Fugaku-like chip. And I use that as kind of the benchmark for a baseline design that would be HPC relevant, that we're not seeing in the cloud or the hyperscale data centers. So it's not something that we can rent from them either. And I can share that IP list with you. And the question is really how would one partition it in a modular way across chiplets? But I have some ideas on that, but I need feedback from you guys.
Got it. Okay, there's some people in our group who are building sort of a cost model for these things.
Yeah.
Okay.
Yeah, and I'm the problem for me is that I'm not sure where it's most fortuitous to draw the line for the inter-die interface. So I'm cautious about saying that I have that list because I don't know what the implications are of choosing to draw that line in a different location. But all of our many core architectures are again self-similar, like this little array. You can tile up a very large chip design, so you could have a chiplet that has a small number of these cores, but it could be modular so that you could build tile those chiplets together to make a very powerful processing element.
Right.
I would have one other question. I think that's 2 slides ago. Sorry for just asking now, but you were talking about the benefits of having IP available and how that tends to be heavily reused.
Yeah.
How do you see the basically with still process nodes progressing? Is that at all a problem if you have IP on a certain node, and is this easily applicable to the next node down, or how much work do you still have to spend to verify it on 3 nanometers versus 5 versus 7?
Well, for example, with PCIe or even memory interfaces, there isn't a huge benefit to shrinking to the next node just because the rest of your chip needs to. So for our SerDes, for our flash controllers, it's actually kind of silly that you'd have to relay out the entire chip in all of these subcomponents, even though the benefit for a lot of those kind of peripheral controllers is minimal for going to the next node. There's a big benefit for the processors and the SRAM, but I don't think it helps to the die shrink for the PCIe controller. Not a huge benefit. So it would be nice if we could shrink things not always at the same time, that I could have a bin of PCIe controllers, and as long as I'm using PCIe Gen 5, I just keep pulling out of that bin. And I only need to go respin when we go to PCIe Gen 6, and not when I decide that it's fortuitous to shrink my microprocessor dies, for example.
Okay, I see. At that point, I guess you do have to go to chiplets though, and can't just just the software IP is not in the end. Right now, the model is still that you have to put it all on the same node, at least when you're talking about how it's done today.
Yeah. These are kind of older slides. This is before I saw the ODSA effort. I mean, I've been with the heterogeneous integration roadmap activity for a while, since 2019, and so HIR it looked like the way that industry was going, but you still had to go to AMD if you wanted AMD's chiplet solution. You have to go to Intel if you wanted to get Intel's EMIB solution, and it still looked like it was not a commodity market, let's say. It was still a monolith. You ended up with a monolithic package, but from a different package from each manufacturer. Now with ODSA, it enables us to think of the chiplets universe very similar to the way that we were thinking about the licensable IP universe, but now it becomes not just an IP block. We have to think about the chiplet that you put that IP block into. And so these slides don't fully cover the fact that we think that this open marketplace of chiplets is even better for us than just the open market for the licensable IP, because you still have to balance clock trees and do power delivery. It's not easy. It's even with the licensable IP, it isn't turnkey. So anyways, we're basically want to use get commercially supported IP where there's a market to support it, but use open source IP where the government needs to develop technology that serves our needs. But taking it to the next level, if we could package up these things in the chiplet form, that would be even better for creating a new sustainable economic model for HPC. And this is the reason why we're also concerned about this. This is a recent article published by Dan Reed. You can find it on arXiv. But we have, over the past decade and a half, I was deputy director of hardware technology for the DOE's $2.5 billion exascale computing project. And in that project, I and my cohort, Jim Ang, we invested about $390 million into, Intel, IBM, HPE, Cray, when it still existed, in order to bend their technology in a direction that would enable us to hit our exaflop target in 2022. But now, when we look at the market, the current competing companies by market capitalization, the bottom of our Branscombe pyramid is no longer here on the left. The bottom of our Branscombe pyramid is whoever's supplying these technology companies that are on the right-hand side. And so to the extent that OCP and ODSA are creating an ecosystem that could potentially supply these players who were really controlling the broad base of our computing ecosystem, we want to figure out how to leverage that part of the market in order to create the new 80-20 rule that would enable us to continue to sustain HPC as a differentiated product line. So yeah, again, Branscombe pyramid, but we're rebasing the Branscombe pyramid. And so we're really looking at alternative economic models that could be sustainable. Our old school models were, sustained partnerships, but we're looking at inverted procurement models like the Open Compute project that might actually enable us to better leverage what's there in the ecosystem. Let me just check the time here. Okay, I'm going to do one last thing. I'm a researcher. We do prototyping occasionally. We don't always need to do a full prototype in order to make our point, but when we do, we tend to get our MPW run. It's a typically small die. We put it on a daughter card and we plop it on top of this FPGA support board in order to give us our memory interface and our IO interface to the outside world. Or even worse, our friends at Columbia University, there's a tiny chiplet here in the middle, photonic chiplet, and all the rest of this is the peripheral testing equipment that we use. And so we typically end up with tiny chips for our MPW prototyping run, and we also don't have the space to really put things like memory and PCIe and all the other stuff you need onto our tiny chip. We're hoping that we could, do something with chiplets that would overcome that, where, if we could in the chiplet ecosystem, get a lot of those IP subsystems like the bootable Linux OS cores, PCIe, and the memory interface, and then we can plug our chiplet to a bundle of wires, AXI4 interface to interface with that, with a commodity chiplet. That would be great. So, we could have our little chiplet array that we use for our accelerator, but we could use somebody else's, Linux OS or host cores. We'd love it if there was like somebody created chiplets for memory controller, especially for high bandwidth memory, because that's very tightly wound. We could put some of our stuff in there to augment the memory, to do our gather scatter type stuff that I was talking about earlier. And we also have our friends at Columbia University. They've created a photonic co-packaged memory that works already now with PCIe. I mean, this would be great for us in the prototyping community to be able to leverage chiplets in this way. This here is an example. I know you guys have an interest in co-packaged photonics. This is already taped out and it's running right now, but it's wire bonded. This is Columbia's dense wave division multiplexed silicon photonic transceiver platform. It's already got PCIe. All we need to do is figure out how to bump map this and make it speak the ODSA bundle of wires protocol. We've got the PCIe, but we'd love to respin this chip. Columbia, Karen Bergman, would love to respin this chip using ODSA's bundle of wires if any of you guys are interested in doing that. Yeah. So anyways, so this is another. I'm trying to get the DOE to be invested in kickstarting a multi-supplier open chiplets ecosystem, doing a kind of demo like this. And so if there's interest in that as well, I'd love to introduce you to the DOE folks, because we have something called a Research Evaluation Prototypes program that could fund a demo, capability demonstration like that. So anyways, that's the end. Any more questions?
Good timing first. So you're they actually have two questions. One is you're basically saying, if I understand it correctly, if anybody on the call or anybody at ODSA is interested in building specific chiplets, you might have some funding, or you might be able to round up a consortium to fund that effort.
Yeah, if we could come up with a good story. Right now I'm being asked by the NSA to come up with a really good prototyping story. We have to include some of the stuff that we've developed over the past couple of years, you know, that semi-custom stuff that I was talking about, but we'd also like to do a demonstration of a multi-vendor chiplet based SoC, and if we can come up with a very specific cost and schedule for that, I think I could probably get them to co-invest in this.
That is good to hear.
Are there any limits on technology? Like are there? You mentioned 14 nanometer is smallest you can build.
That's our limitation. We basically are Synopsys license. We only got down to the 14 nanometer PDK. A lot of that has to do with DARPA, the MPW runs that they prepaid for with TSMC were for the 14 nanometer line. That's more to do with that than anything else. And that's just for our own capability to create MPWs. That's the PDK that TSMC is allowing us to use. But that's because of DARPA. Okay. But I don't think that's a general limitation.
I had a question,
Okay,
John.
Sure.
Your second bullet says kickstart a multi-supplier open chiplets ecosystem. How do you resolve all the multiple different die-to-die interfaces and newer ones come in every day?
Yeah. No, I mean, we're really hoping that we could rally around something like you know, the bundle of wires, you know, die-to-die interface. That's why I'm here. I'm interested in the UCI Express. I'm also interested in seeing how that's coming along, but also on bundle of wires. You know, it's able to tunnel AXI and PCIe. And that's a good start. But I don't know how far along you are in qualifying your electrical interfaces to demonstrate that these are truly interoperable yet. I saw the, you know, stuff from Bappy's slides of the Jayhawk, you know, die-to-die chiplet demonstration, and I'm just hoping. I don't know how far along everybody in this ecosystem is, but if we could choose one bundle of wires standard and agree that that's what we'll build this demonstration around, this wouldn't be a production scalable product. We're talking about if a proof of concept.
Yeah. No, I agree. So for a proof of concept, you just want to pick one and then go with it. But you know, for a true ecosystem to exist at some point, it might be more useful to have just one or two players or one or two prominent ones that everyone can subscribe to.
That's true too. If we had anything that shows two different vendors putting their stuff into the same package, that's a win.
We actually might have that.
Go ahead, Bobby.
No, I was you or JP, one of you guys, but we actually have a test chip package doing exactly that.
Yeah.
Trying to do exactly that. And unfortunately, we're almost out of time. So there is a Wednesday meeting, not JP, you're meeting Wednesdays, right? At 10
Wednesday,
a.m.
10 a.m.
Wednesday meeting at 10 a.m. Pacific, where they're actually, JP is actually working through along with a bunch of participants on the mechanics of getting two dye from two different companies to interoperate. And maybe someone from your team could attend that.
Sure.
At least you get a sense of.
Add me to the invite. I'll try to make it. The other part of this, though, is that in order to get NSA involved, we'd have to have take it to the next level where we have two vendors, but that the U.S. government has to figure out. We have all of our Verilog, and we can do Verilog to GDS, but we don't know how to do all the other steps, like to get the correct electrical interface so that we could also plug into your demonstration, for example.
Right, and then the second sort of related thing is that April 26th, we will have a talk. There'll be 10 vendors discussing specific products and prototypes with interfaces by the ODSA. So this is a fairly diverse range of products. So we'll have 10 companies talking about it.
Yeah, I'd love to attend that, and I also would want to bring in, so the DOE side is also planning and putting out an RFI about getting advice about where we should start investing our, research evaluation prototype. This is separate from the NSA thing. So whereas NSA has money now, the DOE is trying to figure out what it's going to do in FY23, and they're going to put out an RFI, but they'd like to meet with consortiums like the ODSA to figure out what exactly is going on here, because I think they don't have much visibility into it. They need to understand it before they figure out if they want to play.
Hey, John, this is Cliff Grossner. I'm with the foundation itself, and this could be something that I think the foundation itself, which supports many projects, but certainly this is a very important project for us, would want to get engaged to help with if we could. And
yeah,
so
no,
please.
I want to get you guys together with the DOE people.
Right, and in support of this project, I'd probably like to bring in our CTO and see where this is going to go. If at some point there's going to be a push for funding, then if the OCP itself can lend a hand, we probably would want to.
Yes, well, we really want to see this happen. We know it won't happen if we don't participate, but we can't do it alone. And so we would definitely want to work. This would need to be a partnership for it all to work.
Okay, then let's explore what we can do.
Okay, yes, please reach it. Shoot me an email. I'll try to get you connected up.
All right.
Okay.
On that wonderful bright note, John, thank you so much. And everybody have a great weekend and everything.
Great, thanks.
Hey, thank you.
Thanks. Bye.
Bye.